This is my extremely low quality video about dependent versus independent t-tests. So first thing that I would like to do is to take you through a tour of what I already have up, and then we can explore together the differences that occur when we're computing an independent t-test versus a dependent t-test. Okay, so first things first, anything on this panel here is relating to computing our dependent t-test. This is the data with some descriptive statistics already in place. Hiding down here are some critical t-values that apply to, well, this critical t-value applies to the dependent t-test. This critical t-value applies to this independent t-test. By the way, this is where the independent t-test computation lives. So I've written down some formulas. And the data here, so group 1 has observations 1, 2, 1, 3, and 5. Group 2 has observations 2, 3, 2, 5, and 8. And so what we're doing is we have these two groups, and I haven't really specified whether these are paired data, meaning that there were 5 participants in total, each giving 2 different data points that match up, or instead, if there were 10 participants total, 5 randomly assigned to group 1 and 5 randomly assigned to group 2. So depending on the situation, we would use a dependent or an independent t. And I feel like some of the stuff that one is trying to learn in these kind of like 300-ish level social science stats courses is about really why is it that you need so many more participants, or that you need a larger sample size in order to have enough power for your independent t-test versus your dependent t-test. And the formulas about how to determine that sample size are not here, but this might help us to understand a little bit what the mechanics are going on, and it'll help us practice t-tests also. So that'll be nice, bonus. So yes, this column marked D, are the different scores between group 1 and group 2 as if the data were paired, because we're going to need this different score data for our dependent t-test. So assuming they were paired, we could create a different score column by hand, and we would go 2 minus 1, 3 minus 2, 2 minus 1, 5 minus 3, and 8 minus 5. Cool. The means and the standard deviations of these 3 columns are right here. So I've already computed them, hopefully correctly. One never knows though, so if it's not, then let me know. So this is the mean for group 1, which is 2.4. And the standard deviation for that group, it's denoted by an S. I try not to use SD, although sometimes it happens. So S for standard deviation of group 1, 1.67. Okay, mean of group 2 is a 4.0, so this overall looks like the numbers are larger, at least according to the mean. And then S2 is standard deviation for group 2, and that's 2.55. So I calculated those behind the scenes, so you wouldn't have to bother ourselves with them. But if you forget how to calculate a standard deviation, give it a try, and then you can verify these numbers also. And then here the different scores also get their own mean for the dependent t-test calculation and their own standard deviation, which is denoted by S with a little capital D as a subscript, the standard deviation of the different scores, and that is 0.89. Okay, for our dependent t-test, the top looks like the difference score mean minus mu. And the thing about this notation is it's trying to say we want to compare the differences to as if there was a difference of 0. The difference of exactly 0 being the null hypothesis. So it's set up like this, where you put the mean of the different scores here and then you subtract 0. That's the convention. So that is going to be equal to 0 because it's just talking about the difference in means. And then yeah, between the data that we have and what the null hypothesis would be, which is 0. And then if you look at the independent t-test, I didn't write the null hypothesis part out because it's not in our formula sheet. So I guess we get to dispense with that. But there's an equivalent kind of extra mu stuff here, but it's cool. Like, we're cool. Don't worry about it. Just use all the formulas the way that we've been using the formulas. Anyway, I don't have enough room. So we have this t-test is comparing the difference in the two groups as if it's two different groups of different people. And then there's this funny looking kind of, this is a standard error calculation, but it's interesting because it's got the two standard deviations in them, and then they're divided by their ends, and then but they're added. And this one only has one standard deviation. And so that's kind of the difference that I wanted to point at. Because as we go through, we'll be able to see like which numbers are bigger and where, and then we can understand more about dependent versus independent and how it works. So if you're lucky and your N1 and your N2 are equal, which they are, our N1 and N2 are 5, all the n's, little n's, are going to be 5, then you end up getting a t-test that could be written like this. You've not seen this though. This is just a kind of a different way to write it if the n's are equal. And I think what it does is it lets us compare the two t-test formulas just a little more easily, especially when we get numbers in them both. Then if we start with this formula, it's just the bottoms rearranged a little bit. Wait. Oh, I think there's a problem with it. So like, what I did was I like split up the square root sign, and then N1 and N2 were equal, so I called them N, and then I forgot to put the squares up there. So bad. Okay, so let me change that. So S1 squared plus S2 squared. Yeah, apologies, that looks better. Okay, so without further delay or embarrassment, let us calculate our different t's, and I have a calculator because I can't do the mental arithmetic necessarily. So for this one, we know that this is just going to be set to 0, and in fact sometimes people don't even write minus mu, they just write difference score, and the difference score mean is 1.6. Okay, and then we divide by the standard deviation associated with the difference score, so it's 0.89, but that itself on the bottom is divided by the square root of n, and n is 5. Because for the dependent t-test, we have 5 participants in total, or at least we're pretending that we do. What a horrible experiment. Well, okay, it depends. Now I feel bad. There's certain times when 5 participants works really, really well. I'd encourage you to like try and think of something. Like, it's a bit of maybe a tricky question, but yeah, so okay, in some cases it works. In this case, it's not very good, but it's good for an example. Okay, so then this is how it's all set up. I'm just gonna leave it like this. Because then I'm going to come to this t, which is their independent t. So now we're assuming that we have 10 participants in total, but little n is still 5 because it's per group. And so we have x2 minus x1. And x2 is 4.0 minus x1, which is 2.4. And lo and behold, when you calculate that, you end up getting 1.6. Now I'm nervous. Is it 4 minus 2.4 is 1.6. Okay, cool. Okay, then we have to divide by this funny looking thing divided by the square root of n, all on the bottom. So it would look like the square root of s1 squared, so 1.67 squared, plus s2 squared, so 2.55 squared, and then that whole thing would be divided by root 5. So see, they kind of look similar, except that this part of the denominator is going to look different once we get it close to looking like the form of this, because this is almost ready to calculate right away. This one needs some work. So this would be 1.6. This would be 1.6 up top, And then we would divide that by the square root of, actually, you know what? I have a calculator, so we can do it all at once. So let's go, 1.67 squared, and then plus 2.55 squared, and that equals 9.2914. And then what I'll do is I'll just square root it like magic in the calculator. Okay, so then this part of the denominator simplifies to it's 0.48, but we'll do 3.05 because we seem to be rounding. Okay, so, and I still divide this by root 5 before going 1.6 divided by this part. It's kind of a order of the way we do it. But if you look at this expression here and this expression here, so the independent t-test, this number is bigger. The root 5 is the same because it's 5 per group, and it's 5 per group. It's just the same 5, giving data twice. And then it's 1.6, which is the difference in means. And so we get 1.6 for the different scores there. And then when you do it by hand, it's there. But the issue is this, it's the way that we're computing the standard deviation. So this here, this is the standard error that goes with the dependent t-test, because your t-test is difference in mean over a measure of spread, which becomes our standard error. That's what it is. And then here, difference in means over standard error. So this standard error here is bigger than the standard error here. It's the same data, but the way we're looking at it and interpreting it is different. Okay, so now I want to see what the t-value is. So it's 1.6 divided by whatever that is. Okay, if you're bored, I should have said this, like, just skip ahead if you're not already doing that. And then, so we're going to go 0.89, and then we're going to divide that by the square root of 5, and I'm getting 0.398. I'm going to keep that. You know, I get a little nervous with little numbers. I want to keep more decimals for some reason. You can keep 2 or 3 in your calculations, whatever you're more comfortable with. And then for this one, I'll have to continue it all the way down here. So that'll be 1.6, and we're going to divide by whatever this is. So 3.05, and we divide by root 5, so we divide by, Okay, so this quantity is 1.364 to 3 decimal places. So now we can take a step back and I can show you, okay, like just ignore the root 5, but like take a look at this box and take a look at this box. Can you predict which of these numbers is going to be larger? You see, because when the denominators of numbers, so this is a standard error still, when the denominators of numbers are little, they actually make the number itself bigger. So dividing by a bigger number for this standard error calculation means that it's going to be something smaller than this thing. Oh, sorry, I said this was a standard error. It's not. It's the t-test. This is the standard error. This one. Here, I'll label it so that, so it makes more sense. Oh, all right. This is the standard error. Yeah, and this bit is the standard error. The 1.6 isn't part of it, yes, because we simplified. Okay, I ran out of room. And maybe time. All right, so what we're going to do is just divide. So 1.6 divided by 0.398. Okay, and that's equal to 4.02. That's a nice, solid, big T. Well, it's a little t, but it's like large in magnitude. Okay, and then for this one, we really are running out of room. So we'll just say equal sign from here, and then we'll carry that calculation ahead. So that's 1.6 divided by 1.364, and that being larger than 0.398, we end up getting 1.173, so 1.17. Okay. Now, I've already circled everything a million times, so I don't know how to indicate that this is the important number that we're focusing on. Oh, I know. Yeah. Make everything else go away. Yeah. So 4.02 is our t-value for the dependent test interpretation of these data, and then 1.17 is the, ooh, my whiteboard moved, is the interpretation where we pretend we have two different groups of different people. So 1.17, I'll put that down again for you. Yeah, so the calculations are gone, but the formulas are still there, and you kind of saw how when you were able to manipulate it a little and go step by step, they look almost the same, but because the standard error is calculated in this way, why is a theoretical question, so we don't need to get into it right now, and it's a little complicated, but in general, we in psychology do take it for granted, but when the standard error is calculated in this way, it makes it larger, which makes the whole t smaller, which I already repeated, so hopefully you're not too bored and irritated, but we can see then, if we're doing a dependent t because we have the same participants in both groups, then we'd end up with t of 4.02, and the critical t from the table that I looked up, with the degrees of freedom being 4, because there's 5 people in the 5 people in the study, or 5 data points in the study overall, that is 2.78 rounded to 2 decimal places. So this would be a significant effect. So we could say something like p is less than 0.05. This is like pretty crappy formatting, but it's rough. This isn't like a journal level formatting. And then here, if we compare 1.17 to the critical t using 8 degrees of freedom, because the way that we do degrees of freedom is n1 plus n2 minus 2 when we're doing an independent t-test. So that's 5 plus 5 minus 2, or 8. Then we get this critical value. So it looks like this critical value exceeds the observed value. So then in this case, p is greater than 0.05. It makes a difference. And so maybe that's like a little bit helpful in terms of how the dependent t-test is working compared to the independent one. It's not quite doing the same thing because the formulas are slightly different, and they end up creating larger standard error here due to the fact that you've got 2 different standard deviations and they're both squared, and then they end up getting added somehow. So that is it, and it's awkward because I have to manually turn off the video. Okay, bye.